In class, we were doing a computation and we're computing a surface integral over a sphere of radius 3. And I said I thought I'd made a mistake and I couldn't figure out what it was. And I found it pretty quickly after we left class. So I thought I would just go over that mistake and maybe add a little bit of information to what we were up to. So we had a parameterization, r of uv, 3 cosine u sine v, 3 sine u sine v, 3 cosine v. And that parameterization is a parameterization for a sphere of radius 3 centered at the origin. So this is related to spherical coordinates where we're using u instead of theta and v instead of phi. Alright, so the computation we're trying to do is compute dr du cross dr dv. And here's where I made the mistake. So when you compute dr du, the derivative of cosine is minus sine. The derivative of sine is cosine. But then when you look at the k component of this vector, there's no u's there. That should be 0. And I'm pretty certain I got something that was not 0. And that's going to make a big difference in our computations and how they simplify. Dr dv, the derivative of sine is cosine. Derivative of sine, cosine. Derivative of cosine is minus sine. So these are now the correct partial derivatives dr du and dr dv. Now we want to compute that cross product. So as for the I component of the cross product, you multiply the j with the k. It gives us this. Subtract the k with the j going this direction, and this one is 0. So I didn't have 0 here before, and obviously this is a lot simpler than what I had. When you compute the j component, you multiply I with k, and there's this minus sign out front, gives you this. Subtract k with I, 0. And then for the k component, we get I with j, j with k, gives us this. We can simplify this a bit, so just multiplying this out, we get this. Multiplying this out, we get that. And here, there's a common factor of minus 9 sine v cosine v. If you factor that out, you get sine squared plus cosine squared, which is 1. So here's the final simplified version of dr du cross dr dv. And when I did this, I made an observation that there was a common factor of minus 3 sine v. There's actually a minus 9 here, so you might wonder why I took the minus 3 out instead of a minus 9. We'll see that pretty soon. If you take minus 3 sine v out, you're left with this. Well, what's interesting about that is actually exactly what we started with, RUV. So it turns out that dr du cross dr dv is minus 3 sine v RUV. And I'm going to make use of that now because what we really want is the magnitude of that vector. So the magnitude of dr du cross dr dv using this version is, well, this is a scalar. So it's the absolute value of that scalar times the magnitude of RUV. But RUV is a vector whose tail is at the origin and the head is on the surface of a sphere of radius 3. So the length of that vector is 3. Absolute value of minus 3 sine v. V, remember, is the same thing as phi. And phi ranges from 0 to pi. And in between 0 and pi, sine of v is positive. So the absolute value of sine of v is sine of v in that range. And the absolute value of minus 3 is 3. So what we end up getting is 9 sine v. And I want to observe a couple of things about this actually. One is that the radius of that sphere is 3. So this is actually the same thing as the radius squared sine v, or rho squared sine v, which may look familiar. That's actually the integration that we use when we do integrations in triple integrals on spherical coordinates. It's not a coincidence at all, and that's related to the following idea. Remember that this thing right here, the magnitude of dr du cross dr dv, is supposed to be actually an area of a surface area. That was redundant. So I'm going to go back here and look at my picture. And oh, there we go. Okay, so here is a sphere, radius 3. U is theta, so U has us going this way. V has us going this way. So dr du going this way is a tangent vector, tangent at, say, this point right here, going this way. And dr dv, as v increases, you go down, so dr dv is pointing that way. And if you take the cross product of those two vectors, remember the cross product follows the right-hand rule, so ignore the handbrace. Right-hand rule, you curl dr du going this way, and you would be pointing in. So dr du cross dr dv points in towards the center of the sphere. Okay, that's interesting. That explains this minus sign. It's the inward pointing bit. It points the minus sign here, minus 3 sine v times ruv means that this vector points in the opposite direction of r. R points out from the center towards the sphere. Dr du cross dr dv points in towards the center of the sphere. And here's the other interesting bit. Dr du cross dr dv only depends on v and is sine v. So why is that? Well, one, notice that if you move in theta this way, this is supposed to be the area of a small patch of this surface, right? Well, as you move this way, if you take a little tiny patch around a point and then move this way and take the same patch, the size doesn't change. But if you move this way, notice that these patches are not as big as these patches. So as you come from the z-axis and come down to the equator, those patches get bigger. But then as you move past the equator, those patches start to get smaller again, right? Well, notice what's going on with sine of v. You start at the z-axis and those patches are very small, in fact 0. So up here, those patches are very narrow and 0. And then as you move towards the equator, they become almost a rectangle. So it's almost the case, it's right here, it's the case that a little tiny patch here would look like a rectangle. Du and dv would mean the same thing. And that's here at the peak of sine of v. And then as v goes past pi over 2, as you go back towards the negative z-axis, then sine of v starts to decrease, these patches start to get smaller again, and they start to look less square-like, so that du, well, du is actually decreasing, right? Here it's this length, and then as you go here, it's this length. In other words, as you change in v, this thing is not a square or a rectangle. So I think it may have made that less clear than it was before. The idea again is that this thing measures an area of a small patch, and that small patch is very small up here, it's very narrow, it widens up as you change with v and then narrows again. That's what that represents. But here's what you should know. You should be able to parameterize a sphere with radius 3. You should be able to compute dr du and dr dv. You should be able to compute this product, cross product, and you should be able to compute the magnitude of that cross product. You might not do it the same way I did. You might just go ahead and plug these components into the formula for the magnitude of a vector and compute them directly and not be quite as fancy as I was. That's fine, but you should be able to do those computations.